Good morning, everybody. We're going to pick up in our notes from the last time and do the second half of the notes. We've been looking at the behavior of gases, the last section in chapter 14. Last time we looked at Boyle's law. We've learned that a gas can be affected by the temperature, the pressure, or the volume that the gas has. And if you change one of those, it can affect the others. Well, last time we looked at Boyle's law, where if you keep the temperature constant, the pressure and the volume affect each other. Now, this time, we're going to look at another law. This particular one was discovered by a French scientist named that's his last name, named Jacques Charles. Okay? So we're going to look at Charles' law. We just say Charles usually, okay? Charles' law. Basically, it says, if we keep the pressure of a gas constant, now remember, there's three variables: pressure, volume, temperature. And you have to keep one of them constant while you look at the other two. In this case, we're going to keep the pressure constant and look at the volume and the temperature. He discovered that the volume of a gas will increase as the temperature increases. So let's go back to our cylinders with a piston and gas inside. If you heat the cylinder a little, the gas absorbs some heat energy, but not a lot. So that means the heat energy absorbed doesn't create a lot of collisions, and therefore you don't the particles don't push up very hard on the piston. Therefore, you don't get a lot of volume. But if you heat up the gas a lot to a much higher temperature, the particles will have much more kinetic energy and therefore collide with the piston and the walls and more pressure. Not more pressure. When they do, since it can expand, they will push up harder because they're colliding faster and you get more volume. The pressure remains constant. And therefore, the greater the temperature, the greater the volume is when we keep the pressure constant. Okay? So we're saying as the temperature increases, and here's where we have a typo. I forgot to fix this on the computer, and I apologize for that. That should be a V, and this should be a V, okay? Because we're looking at temperature and volume, not temperature and pressure, although we could, but we're not. So as the temperature increases, here to here, the volume increases. And we could go the other way. We could take the heat away and allow the gas to cool. It's going to lose some of its energy. Therefore, you're not going to get as much collisions, forceful collisions against that piston. The piston will drop, and therefore the volume decreases. So if the temperature decreases, the volume likewise decreases. If we graph the relationship, we get a linear graph, a straight line graph. So going this way along the line, you have increasing temperature and increasing volume. But if we go this way, we have decreasing temperature and decreasing volume. All right? So if one increases, the other increases. If one decreases, the other decreases. That was a little different from Boyle's law, where one increased and the other decreased. They did the opposite of what the other did. Here, they do the same thing. And please remember, we are keeping the pressure constant, okay? Now, let's talk about an application of that. I don't know if you guys have ever ridden in a hot air balloon. Did you know you can actually do that? There are companies around here in Florida where you can go up in a hot air balloon. That's kind of cool. I've been thinking about getting a hot air balloon ride for my husband's birthday. We'll just have to see what happens. But in any case, what they do is to inflate the balloon, they put air in the balloon, but then they heat the air up. The hotter the air becomes, the more energy it has, and it pushes out on the sides of the balloon. Now, you'd think, well, that makes the pressure increase. Not really, because the balloon's walls, like the piston, they're movable, they're expandable. So the pressure doesn't actually increase, but the balloon sides, the walls of the balloon expand as the air gets hotter inside the balloon. And because you have the same amount of particles inside the balloon here in both these places, but these take up much more volume, that means the density here is much less than the density here, and the balloon travels upward. Okay? That's kind of cool. So hot air is less dense than colder air and will rise. Okay? So that's what we're doing. We're heating the air. That causes the volume of the balloon to increase because the walls will expand with the collisions. And then less density because you have the same amount of matter for a much bigger volume. It rises through the air, which is kind of cool. And I think that would be a cool Christmas present. He'd like that, I'm pretty sure. Now, there is also a way, just like with Boyle's law, there's also a way to calculate unknown temperatures or volumes using Charles' law. There's an equation for it. Okay, so let's take a look at what that equation is now. In this case, it's a little different from the other one because we're talking about volume and temperature, and they do the same thing. One increases, the other increases. So we write the formula like this. The initial volume and over the initial temperature, that ratio will be the same as at any other point in time. Okay? So if you have an initial volume and an initial temperature at one location, all right, you're going to get a certain ratio there. If you increase the temperature by a certain amount, you're going to increase the volume by that certain amount also, so that the ratio will stay the same as the other one. And because of that, we can use this to find unknown quantities. Let's take a look and see how we would do that. Now remember, the first thing we do is read the problem and underline the information that we can see. We have a balloon filled with 2 liters of gas at room temperature, which they tell us is 20 degrees Celsius. Ooh, and I need to mention something about that in a minute, but let's finish. So this is the initial state, because then look what they're going to do. They're going to place it in a refrigerator. That's a different location. So that means the volume and the temperature right now are the initial state. So I'm going to mark that. Here's the initial volume, and here's the initial temperature. Now then we're going to place it in a refrigerator, this balloon, and you can actually put a balloon in the refrigerator and see this happen. The refrigerator is at 3 degrees Celsius, and that's, I think, about 45 degrees Fahrenheit, 40 degrees Fahrenheit, something like that, 40 to 45. Now, this is the new location, so this is the new state, so I'm going to call this the final temperature. And we want to know what is the volume of the balloon in the refrigerator after it cools. So this is the volume associated with the new temperature, so this is the final volume. Okay, now I want you to notice the temperature is going to decrease from 20 to 3 degrees Celsius. So according to what we saw up here, if the temperature decreases, then the volume should decrease also. So when we find our final volume, we should see that it's smaller than the initial volume of 2. We should get something less than 2. Keep that in mind. Now, the little item I needed to mention about the temperature that I had forgotten about. I don't know why it slipped my mind. It just did, because it is written right up here. Whenever we use Charles' law, there is a stipulation. Whenever we use it, the temperature has to be in Kelvin. So the temperature here needs to be measured in Kelvin, and the temperature here needs to be measured in Kelvin. Well, good grief, we've got Celsius. How do we make it Kelvin? Well, we actually learned that in the chapter 1 back in first quarter. If you want to convert Celsius to Kelvin, here's what you do. To get Kelvin, you simply take your degrees Celsius and you add 273. Okay? 0 degrees Celsius is the same thing as 273 degrees Kelvin. And a single Celsius degree and a single Kelvin degree are the same size. There's just 273 degrees between 0 Kelvin and 0 Celsius. So if you say take the Celsius and add the 273, you get the Kelvin. Okay? We learned that already, but this is just a reminder. So right here, we need to convert these. So our initial temperature is 20 degrees Celsius. So we're going to add 273 to that, and that makes our initial temperature 2, and 7 is 9. That'd be 293 Kelvin. That's what we're going to use in the formula. Okay, let's do this one. Our final temperature is 3 degrees Celsius. We add 273 to that. So our final temperature in terms of Kelvin, 3 and 3 is 6, we get 276 Kelvin. All right, so see, decrease in temperature, isn't it? So we should see a decrease in volume. Now, let's look at how we use the formula. Now, this is very similar to what we did with Pascal's principle and hydraulics. We're going to use the neat trick that we learned, cross multiply and divide, okay? So let's start out right here. We've got V sub I over T sub I equals V sub F over T sub F. Now, what is it we're looking for? Remember, we're looking for this right here. Keep that in mind. So we're going to cross multiply. So we get Ti times V sub F equals Vi times T sub F. Cross multiply. Now, here's our unknown that we're wanting to find. Now it's almost like the Boyle's law now. We want this, we need to get this to the other side. It's being multiplied, so we're going to divide both sides. The opposite of multiply is divide. So always do the opposite to move something to the other side, okay? Always do the opposite. There we go. Now we have VF equals V sub I T sub F over T sub I. Boom, there we go. See? We've got these three things, now we can find our answer. So the initial volume was 2 liters, and the final temperature was 276 Kelvin over the initial 293 Kelvin. Oh, now look at the units. The Kelvin will cancel out and leave behind liters of volume, which is exactly what we want because we're measuring volume here. We want the volume. So if we take our calculators, all right, let me clear that. All right, we get 2 times 276 Kelvin. All right, and we're going to divide that. There, now you can see it. Divide that by 293. Whoops, I got one too many 9s in there, don't I? There we go, 293. Enter. Oh, look, we get 1.88. All right, and let's round that to 1 decimal place because our initial volume was given to 1 decimal place. So that would be 1.9 liters, and it is less than 2. So there you go. The volume decreased by 0.1 liter, didn't it? So the molecules of the gas are closer together in the refrigerator because the volume, the sides of the balloon shrink a little bit, okay? There you go. That's how we use Charles' law. As long as the temperature is in Kelvin, everything works out fairly easily, okay? Nice little math tricks, too, that you learned. All right. I'll talk to you later, and see ya. Bye-bye.